All right. So good evening. Let's get started. Today's topic is network communities. So in fact, this is a topic for next 3 lectures. Today we'll sort of have a broad introduction to communities and to sort of ideas, to definitions. And we'll look at 2 methods, 2 very, very simple and intuitive, but at the same time, heuristic methods of finding communities. Next lecture, we'll devote to some linear algebra and ways to actually build pretty strong algorithms for network communities. And the last lecture will be about overlapping communities and some other ideas related to actually numerical computations on the communities. Okay, so we're going to talk today about cohesive groups, and I'll give some definitions, and we'll talk about graph cliques, and we'll discuss why cliques in their normal social scientist or computer scientist discrete mathematics definition is not a good definition for us to use as a community. So we'll talk a little bit about k-plexes, k-cores. And later at the seminar, you will learn more about k-cores and how to compute them. And then we'll actually switch to network communities, and we'll discuss 2 main ways to actually find them. One through similarity-based clustering, based on the ideas we developed in the previous lecture on the structural similarity between nodes. And then the major way is through graph partitioning. We'll start this topic and we'll continue on with it next lecture. So network communities, by looking at this network, and in fact this is a network of collaboration of co-authorship among professors at one of the universities, you can pretty much intuitively see what communities are. So you probably, each of you realize that something like this is probably a community, right? And maybe this is a community, and this looks like it's a community, and this is a community. This is probably a community. Of course, this one, completely separate, is a community. It is harder to find communities in the rest of the graph, but you can probably also sort of decipher that there is some community in here, and maybe something here, and maybe something here, and here, and here. So what we have just done, we partitioned the graph into communities. In fact, this communities corresponds to different departments of the university. Well, we didn't know that. We didn't have labels. The idea would be to actually being able to detect those communities just based on the graph structure. And again, if you think about this, purely intuitively, what I was doing here, I was looking for a group of nodes that are kind of tightly connected between them, and maybe less connected to the rest of the nodes in the graph. So that's, in fact, informal definition of the community. And we'll try to get to that definition through a few examples. So couple points. In this lecture, we'll be considering, first of all, undirected graphs. There are a lot of things that can be extended to directed graphs, but for simplicity, we'll stick with undirected. And the other thing is we're also going to look at the partition of connected graph. Well, the reason for that is because it's sort of obvious and trivial to select this community, which is separated from the graph. So before using any of the methods that we're going to discuss today, if you are given a graph, you should first run connected components algorithms and work with connected component, right? If connected component algorithm returns you a bunch of components, well, each of them can be a candidate for detecting of network community. All right, so the problem of finding communities really originated from, as pretty much everything in this social network originated from sociologists. There is a very good summary in Wasserman and Faust's book, but historically it probably goes to 40s. And the name for the community back then was a cohesive group or cohesive subgroup in the network. And so there are several main properties of this group that people usually look into. Well, first of all, it is mutuality of ties. So the idea that everyone in the group has ties to one another. So if we're thinking about the community, we might want to have connections from every node to every node, right? Something like that. We want to have compactness. Compactness is, in a sense, that it is closeness or reachability of group members in small number of steps. What I have just drawn, this is reachability for every node to every other node in one step. They're all adjacent. But in fact, you might have pretty tight connections with, say, missing one of the links, and then reachability will be can be in 2 steps. For example, from here to here, we get in 2 steps. But again, it's a small number of steps. And then the other sort of thing that we detect looking at the graph on the first slide was pretty much density of edges, right? So there is a high frequency of density of ties within the group, and it is high compared to the frequency of ties among different group members or compared to non-members. For example, if this was one of the communities and that's another community and they're connected like this, well, the average density of ties, which is the number of edges divided by the maximum possible number of edges within the community, will be higher than in between the communities. So these are sort of generic ideas that will allow us to build some more precise mathematical definitions. And so we'll start working with them and see how it goes. So mutuality of ties is really its definition of a clique. So clique is a complete or fully connected subgraph or a set of vertices where each pair of vertices is connected. And again, this is a very nice picture. You can clearly see here few cliques, right? So this is clearly a clique. There is another one here, and there is another one here. Well, in fact, these are not just cliques. These are what's called maximal clique. We'll define it in a second. But clique is a completely fully connected subgraph. So if, for example, I look for a clique of size 3, it really means a triangle. And so then this is also a clique. So on this picture, we'll see the clique of size 5 and higher. But this is a clique of size 3. Well, in fact, every 2 nodes, every pair of nodes that connected are actually a clique of size 2. But we're not interested in that. So the question is, just the definition of clique is not enough to find what we're looking for, because we are interested in things like this. And say this one, though it is a clique, it's for us, it's not a big deal because, well, 3 nodes, but if you take the neighboring nodes, it's not belong to the sort of clique. Well, the formal definition here is the following. Maximal clique is a clique that cannot be extended by including an adjacent vertex. So it is not part of a larger clique. Well, let's take a look at this. So here's a few examples. Well, this is a maximal clique. Well, first of all, it's a clique because there are 2 nodes and they're connected. It's a maximal clique because if we include the 3rd node, what we got is not a clique anymore. It's not a clique because for it to be a clique, there should be a connection in here, but there is no connection like that. On the other hand, if we look at this picture, this is not a maximal clique. Why? Well, because we can add one more node to it, this node, and what we have out of 4 nodes is also a clique. So this clique size 3 can be extended to become clique size 4, and so clique size 3 in here is not a maximal clique. Well, on this picture, this is just not a clique at all. And this guy is in fact maximal and maximum clique. So maximal in the sense that it cannot be extended, and it cannot be extended because the only node we have here nearby is this guy. If we take this guy into account, well, there are some edges missing. For this to be extendable by this extra node, we should have had these connections, but we do not have that. So this is a maximal clique because you cannot extend it. It's a maximal clique, you cannot extend it anymore. And the maximum clique is the largest possible clique in the graph. And so here, this is maximal and maximum clique, right? And quite often there is a, you can define a clique number for the graph, which is the size of the maximum clique. So using these definitions, going back to our previous slide, you can see that that this is a maximum. That's a maximal and maximum clique. These are maximal, and this is maximal clique, right? So 3 of them are maximal, and the largest out of these 3 maximal is a maximum clique. And for example, the clique of 3 nodes is not maximal, because if I add neighboring node, it stopped becoming clique. So this is a definition, pretty strict definitions, but the good news is, well, when you have definitions, you can actually try, you can take a graph and try finding those cliques. Well, there are troubles in here, and troubles pretty obvious, because if you realize what we're trying to do is we're trying to go over all the possible combination of nodes. A little bit later in the lecture, we'll actually calculate how many of those are in there. But the point is that the problem, of course, is, you know, there's a factorial explosion, and the problem becomes NP, right? It is really non-polynomial. In fact, we have a, if the goal is to find a clique of fixed given size k, this is complexity of the procedure. Now, finding maximum cliques, finding maximal, and among the maximum clique carries this complexity. It's where n is the size of the nodes. So the point being that though the definition of the clique is very precise, it's not very useful in the sense of computations. So you can easily detect cliques in the smaller graphs. It is much harder. Well, actually, it's impossible to do in large graphs. But and there is a little but. If we're dealing with sparse graphs, the story changes. And the good news, a lot of social networks are quite sparse. And this is, in fact, the sort of the difference in between, you know, traditional discrete mathematics and discussion of graphs and what we're doing here in network analysis. In graphs or in discrete math, people used to spend a lot of time and building algorithms and finding the complexity of algorithms for, of course, full graphs. In real life, we have sparse graphs. And so things that seemed impossible, they're actually doable in sparse graphs, quite often doable. And there is an algorithm that, in fact, depends on the node degree and number of nodes. So it is not linear in number of nodes, but it's sort of that order of magnitude. And I believe this algorithm is actually implemented in Network X and definitely implemented in iGraph. So there are still ways to find, to efficiently find maximal and maximum cliques in large sparse graphs. And typically, again, we're interested not just in cliques. We're interested because there are just too many, and everything is literally a clique on the graph. But we're interested in maximal and sort of the largest maximum clique. Now, there is yet another problem with this story. Though the graph that I showed you, on the previous slide is really pretty, in real life, most of the graphs are not like that, because the definition is really, really strict. We require connectivity between every single pair of nodes. And that means, especially if you have lots of nodes, all of them should be connected for this structure to be called a clique. And again, in real life, quite often this is not the case. So you'll have a group of people who pretty much everybody knows each other except one person. But if that link is missing, the definition doesn't hold. It's not a clique anymore. And so it's kind of bizarre, because if we have something like this, which looks like pretty dense, but there is one edge missing, well, we'll not consider it as a cohesive group if we think about cohesive groups as a clique, which obviously not true, because it is a pretty cohesive group. So the definition of clique should be relaxed, and we should allow some missing edges. And in fact, there is a definition. And actually, well, first let's find cliques, and then we'll talk about the sort of relaxed version of definition. This is an example of very, very famous social network. It's called Zachary Karate Club. Well, there was a little story behind it. Wayne Zachary was a sociologist who was actually investigating interaction in social groups, and he for several years he's observed the small university karate club and their interaction and friendship, communication between them, and he built a social networks. There was just 34 people. Well, the interesting part that during the time of the observation time, there was some sort of internal conflict or whatever in the club, and the club split in two, with some students staying with sort of original instructor and some students going to another instructor. And the very interesting question would be, okay, well, based on this graph of the social interaction between members of the karate club, would you be able to predict how and where the split occurs, right? And so in some sense, if we could do that, well, that is a result, that would be a result of community detection, because, well, what's communities? Well, right, I mean, based on our definition, it's a group of people that are tightly coupled between themselves, and so you would expect that if the split occurs, it would happen sort of based on a community structure. And again, without sort of going close into the details, just eyeballing this picture, you might think, okay, well, maybe sort of these guys separated out, or maybe there was a split somewhere in here. We got two groups, so there will be one community and there will be another community, so something like that. Well, in fact, if you look in the paper, there is a ground truth in that, so one can compare with it. But before we do that, let's look and study cliques. So in fact, we can detect maximal cliques in this graph, and there are 11 cliques of maximal cliques of size 2, and again, not just cliques, but maximal cliques, meaning that if you add, say here, add a third node, we'll not get a triangle. There are 21 cliques of size 3, and there are 2 maximal cliques of size 4 and 2 maximal cliques of size 5. So let's take a look at their largest maximal cliques, which is maximum cliques. And here they are. So if we look carefully, say these guys, 1, 2, 3, 4, 14, yes, they're all connected each with each. So it is really a clique, it's a maximum clique. And here is another one, it's also a maximum clique. There are a couple points here. First point is, you notice that they overlap. So there are 2 maximum cliques, but they overlap. All right, but they overlap, but they're different. And in social setting, again, maximum clique just really means people communicate with each other. Another point is, though we can find those maximum cliques, it really cannot help. It doesn't help us answer the question of sort of splitting of this karate club into 2 groups. There is no answer to that question on these pictures. What we see is just the tightly coupled groups of students, but and presumably after the split they will stay together. But that's about it. It doesn't tell us anything about the rest of the graph, about the rest of the karate students. So as I mentioned earlier, there is a way to relax this definition, relax the definition of clique, and there are actually a bunch of relaxation. So one of them is what's called k-plex. Well, k-plex is of size n, is a maximal subset of n vertices such that each vertex is connected to at least n minus k other vertices. So in other words, it means any vertex can actually lack ties, but there's no more than k members. Well, say if we have, again, some simple graph, say what it says, if I look at this as a 2-plex, then this will be a 2-plex because, for example, this vertex is missing 2 ties. Well, the way it's calculated is you count as missing a tie to itself here. There is another definition which is also relaxation, but sort of from the different direction, which is called a k-core. A k-core is a maximal subset of vertices such that each vertex is connected to at least k other vertices in a subset. Well, though those 2 definitions, so relaxations do exist, k-plex is, well, quite useless because it also, there are also factorial large number of those k-plexes, and the same way as with cliques, they're computationally hard to find. K-core, on the other hand, happens to be a very, very interesting construction. Well, first of all, because there exist linear algorithms to actually construct those cores. And they became very, very useful, in fact, not for finding of communities, but rather for preparation, for graph preparation, for further processing, for cutting out small edges and finding the actual sort of core of the graph. And today in the seminar, Andrei will talk about it more, and you will do some examples on actually how to find this, how to do this k-core decomposition. But k-core decomposition and k-plex is not an answer for the community detection problem. So before we go any further, any questions about cores and plexes and sort of that discrete mathematics. All right, either I don't hear you or you're quiet. We'll try it again. Any questions? Okay. Well, if that means no, then no. Let's move on. So those definitions were the cliques were too strict for us, and what we actually looking into is something that sort of bridges, this discrete mathematical, very strict definition, and this sort of relaxed understanding of the community that exists in social sciences. And one of the ways to think about this network community is really a group of vertices that are similar to each other. I mean, if they're connected, they're communicating, and they're sort of interconnected, they should be similar. I mean, if you look at this picture, let's say those two nodes, they probably, well, they're very similar in terms of how they're connected to other nodes, and so they probably belong to one community. And again, there is a bunch of nodes here that seems to have very similar connectivity patterns, and they might be a community. And these, say, 4 guys, they are all connected between themselves and also connected to node 1. So they have very similar connectivity structure. And on the previous lecture, we actually talked about structural similarity, right? We talked about structural equivalence, and so the relaxation of the notion of equivalence is structural similarity. And so the idea that we might use is, well, let's just calculate similarity between vertices, structural similarity between vertices, and group together those vertices that have high structural similarity, which means they have very similar or close connection patterns. So in other words, they pretty much connected to the same type of nodes. And it is clear that, again, if we look at this sort of any clique like that, well, yes, this node is connected to this guy, this guy, this guy, and this guy. Well, if I take another node, this node, well, I can do a different color. This node connected here, 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 and here. So these are the patterns. So those 4 nodes are the patterns for the connections. And for this guy, these are the patterns of the connections. These are neighbors. So lots of neighbors. These neighbors, they do overlap, which means the structural similarity is pretty high. Just to point out, so right now we're talking about structural similarity between nodes. We have not assigned any labels to the nodes, though it is clear that we can add the labels and similarity between labels if we have that, and sort of extend this notion of similarity between vertices just from structural to also to include the values of the labels. But at this moment, it's all about graph structure. So based on this definition, if we want to detect a community, it really means we just need to assign each and every vertex to a particular community. So we just need to go over all the vertices and say, okay, well, this vertex belongs to the community 1, to the community 1, to the community 1, to the community 1, to the community 1. And let's say this vertex belongs to the community 2, community 2, community 2, community 2, 2, 2, etc. So go over all the vertices and give every vertex an assignment which community this vertex belongs to. Today, in the next lecture, we'll be looking at non-overlapping community, which means vertex can belong only to a single community, only to a single group. Later on, we'll again relax this condition and will allow for overlapping communities. But today, it's non-overlapping, which means every vertex just have one assignment, and it's sort of strict assignment. So similarities. Well, we talked about it last time, and we can use Jacquard similarity, which is just the number of overlapping neighbors of the nodes. We can go for cosine similarity. We defined it last time. We can go for Pearson correlation coefficient. We in fact can even do Euclidean distance between two vectors, if again they're considered in the space of other nodes. But since it's distance, we can recalculate it into, well, it is dissimilarity, so we can convert it into similarity, recalculate it into similarity by doing either one of distance or one minus. So there are multiple ways to define it. And this is sort of a strength and the weakness of the methods, because different similarity metrics will actually lead eventually to different communities. And the question, which one is correct? Well, it's a very polite question. It really depends on your application. When we're dealing with social networks, you should realize, you should think of which of those similarities actually make more sense. Okay, so after we're done with this, after we're done with selection of similarity, we can calculate similarity matrix. In fact, we did it last time, so you just calculate a matrix of pairwise similarities. Now, again, if the graph is dense, that is that is not very cool. It's n squared size of the similarity matrix, and for each of them, you will have to go. So for each to calculate each and every value, you'll have to go and compute similarities and go through each and every node. So in fact, it's it's literally, if we're talking about, say, Pearson correlation or cosine similarity, it's really matrix times its transpose, and cube computations. So again, it's not going to scale. The good news, if you have sparse matrices, you don't have to do that many computations, and you can also use some certain cutoff parameters. So you'll, for example, can calculate not pairwise similarity between every single vertex, but you, for example, can calculate similarity only between those vertices that are connected, because if they belong to the same community, they better be, most likely be connected, right? Or there are other sort of shingling methods to actually reduce the computational burden in here. But again, building the similarity matrix for large graphs has to be taken carefully and seriously. And after this matrix exists, well, we need to group together vertices with high similarities. That's already sort of no-brainer, because in fact, that is what you do in every clustering algorithm. And whether you want to use say k-means or hierarchical clustering, whatever you want, right? Because you have similarity matrix. So we're going to talk a little bit about hierarchical clustering. Typically, within the social network world, people use hierarchical clustering to do this. So just to remind you, most of you have seen this algorithm from course on data mining or machine learning. The way it works is quite simple. You start by assigning each vertex to a group on its own, right? So if you have bunch of vertices, you assign each of them. Oh, and by the way, they're connected, right? It is a graph. So vertices connected. But what we're going to do is we're going to cluster them based on the similarity. So first we computed similarity metric, then we assigned every node of this graph to its own cluster, and then we start merging those nodes based on their similarity between them. and a similarity based on the connectivity pattern, right? Based on a structure. And so the way it works for like classical agglomerative clustering is first we assign a vertex to a group of its own, and then we find two groups with the highest similarity, and and then the very first step, it's really just vertices with the highest similarity, and join them into the single group. Let's say we detect these guys were the highest similarity, we join them into a single group. We realize next step that this, for example, this vertex has a high similarity to this little group compared to everything else, and we join them into one cluster. And the way we calculate similarity between groups, well, there are three sort of different ways to do it. One is what's called single linkage clustering, which means we define similarity between groups. And again, if we're talking about one node and say three nodes, oh, okay, let's do two nodes in one group and three nodes in the other group, and we're thinking about merging those groups. And if we want to merge them, we need to calculate similarity now between groups. And to do that, we can either use what's called single linkage clustering, which is we select most similar in the group. And if I think about sort of projecting this into low-dimensional space, and the most similar will be like sort of the nearest here, literally the nearest nodes. Or complete linkage is based on the distance, on the similarity between the furthest away, or average linkage means, we just do mean similarity between groups, so all pairwise similarities. Each and every of those methods, have a right to existence. They actually also will provide different clustering schemes. And so the way this works is we sort of iteratively do this and build up the partitioning into the groups. Again, this is just classical agglomerative clustering. If we look at this little picture here, what shows is the following. First, we connect nodes A and C, join together nodes A and C. So this is our little cluster. Then we compare again all their, and the reason we started was joining A and C simply because we compared AC, AB, BC, BD, DE, BE, and AC happens to have the strongest similarity, so we join them together first. Then we again keep comparing every node with every other node or pair, and we found that B is in fact stronger connected to AC than anything else. And then they merged into this sort of extended cluster. We keep going. It happens that D is more similar to E. They're being merged together. And eventually this whole thing gets connected into one big cluster, one big group. And while we're doing so, we can keep building what's called dendrogram, or this hierarchical structure that tells us how things has been connected. So that's, again, very traditional hierarchical clustering, sort of hierarchical agglomerative clustering. The only thing that we have here from social networks is the way we build the matrix. And when we have this dendrogram, we can determine clusters, and to find the clusters, and in this case, clusters will be communities. What we need to do is to cut this, say, dendrogram at some level, and this level will give us, say, if I cut here, will give us two clusters. So that's sort of the very, very basic method of doing it. Here's an example. I look at the same karate club, and we have a similarity matrix, and this is really a correlation matrix. So I used correlation as a similarities metric here. So it is correlation. And the color, it is color coded the following way. The stronger the correlation, the darker the color. So of course on the diagonal we'll have like ones, but there are some blocks here. If you look, for example, down here at this corner, you'll see nodes, say 33, 34. being in a sort of making a darker corner, and these are these two guys, so they're very, very, very similar. You can also look at the nodes right here. You know that there is a 16th, 17th, and there is a bunch of nodes here that have very high similarity, so that they play similar roles in those graphs. So if we do this, then we can just take this matrix and feed it into clustering algorithms, right? Hierarchical clustering. And I used, say, average linkage, and this is a picture I got, and what it shows is there is this guy that has been, for example, merged first, and there is this, and so on and so forth. So as I mentioned, when you have this tree, in order to get clusters, well, you need to select some sort of cutting level on which you split this tree into separate trees. And if I select it up there, well, I'll have two trees. If I selected, say, this cut down here, I will have 1, 2, 3, 4, 5, 6 trees. I'm sorry, 6 clusters. So there is, there is this parameter selection that will give you the number of communities. Again, it's no different from traditional clustering. And here's a picture if we do a cut at this level, and that's what it gives us. Well, in fact, this is very, very good picture, because we kind of looking at first at the beginning. At the beginning, we looked at this graph and we thought, well, this might be a partition, and it just nailed it. In fact, if you notice that this is that group that we detected as a clique, and it stayed together, but it sort of it has been expanded, right, to cover the rest of the graph. Now, there is one thing that I sort of swept under the rug really quickly, is that by hand, we selected number of clusters and to be 2. Right? This is sort of the knowledge that we did not extract from the data. We just said, okay, well, let's be 2. And as always in clustering, this is the trickiest part, is how to select number of clusters. And we'll talk a little bit more about this at the end of the lecture, on like sort of how to use something different from just similarity to detect good clusters. But if we actually go for 3 clusters, and the way to do it is just to select this height on the cutting when you cut the dendrogram, well, that's what we get. Now, this makes much less sense, and it's very clear why the clustering algorithm cut out those nodes. Well, because 34 and 33 has very similar connectivity pattern, and in fact, if you look at the node 25 and 26, they're all connected into here, and these 2 guys are also connected into there. So the overlapping structure of connections are pretty high, and that's why when I start looking for sort of smaller clusters, I get those 2. And so now, yeah, there are 3 clusters, but it's probably not the answer we're looking for. So from the point of view of the sociology, that the best answer was 2 clusters. At the same time, who knows? The team, the club was split in 2 pieces, but there is still some sort of social interactions happening inside, and there are still sort of subclusters or subgroups of people who are much more connected between themselves than with the rest of the club. And in this sense, partitioning into more clusters might make sense. And I would say, okay, well, here is these guys, and here is probably these guys, and here is probably these guys. So maybe, you know, there's a sort of 4 cluster is even a better approximation to the problem. But again, as always with clustering, this, you know, discussion is sort of subjective, right? So you need some external metric to confirm, you know, how many actually clusters you have. Okay, so here we talked about this sort of the similarity-based methods for community detection. This is really conceptually the easiest one, and it's standard, very, very standard in the sense that, okay, well, take nodes, calculate similarity matrix, and then go do your sort of standard data mining. Because now, you know similarity in between 2 nodes, you know, do whatever you want. You want to do PCA, do PCA. You want to do, say, you know, MDS, do MDS. You want to do, you know, clustering, do clustering. You don't want to do SVD, do SVD. Whatever you want to do with it. And we're pretty much done with social networks at that moment. Now, there is another definition. There is another way to think about network communities that actually stays entirely within the realm of networks. And this is sort of the graph language now. We can define network communities, and this is sort of the second alternative definition of network communities, as a group of vertices that are more tightly connected between them within the group than between the group. So this is, you know, to me is much more intuitive definition, because, you know, it's not very clear what similar nodes are, but it is very clear when you're looking at the graph, when you see, you know, dense patterns of connectivity. So by looking at this picture, it is sort of obvious that we have 3 clusters in here, and you know, the number of edges within each of those groups is definitely higher than the number of edges between groups. And to detect these clusters, to find these clusters, what we could do is we could go and do what's called graph partitioning. In other words, we can actually, instead of looking for similar nodes, we can actually start cutting connections. And we can explicitly cut out these edges, you know, this edge and that edge, that pair of edges. And when we do so, we'll end up with 3 communities. Now the question would, you know, remain, well, how do you find those edges that you want to cut? And of course, this is no easier question than we do with clustering. But it is a very different approach in the sense that here we'll be dealing directly with edges, versus on the previous method, we actually looked at the structure of the graph, computed similarity between nodes, and then we sort of operated on the similarity of node similarity basis. Before I move forward, any actually questions about the sort of the similarity approach we talked? Have you done hierarchical clustering before in data mining?
Yeah.
Yes, okay. Okay, good. So that shouldn't be any problems to actually apply it here. And one of the goals would be at some point to actually compare methods, right? Okay, so again, we'll move on by looking at the finding of network communities as a graph partitioning problem. And so we're going to be talking, you know, right now we'll be talking the graph language. We'll sort of shift from data mining perspective to actually discrete mathematics and graphs. And now we're going to be doing graph partitioning. So we'll be trying to find those edges that we need to remove to split the graph into pieces, and every piece would be a community. And sort of overall goal, that the objective we're trying to get would be, okay, find sort of communities. Communities are a group of nodes that are tightly coupled between themselves, and we'll need to cut sort of as few edges as possible out of the graph to see the graph sort of split and fall apart into those groups. So that's the intuition behind what we're going to be doing. And today we'll actually look at sort of another heuristic method of doing so. Next lecture, we'll actually build up a pretty strong theory of how to find those communities consistently. Before we go into this, there's like very important point. The graph partition problem is NP-hard. The reason for that is, again, because it's a combinatorial problem, right? So even if you want to divide, say, n nodes, network of n nodes into 2 groups, it's a factorial number of ways of doing so. Well, the way to think about this formula is very simple. If you have n objects, and let's just think about nodes of the graph. Well, there are n factorial ways to arrange them, right? N factorial ways to arrange them. And now, if we want to split it into 2 pieces, say do bipartitioning, let's say we do it here, then you can exchange places of all the guys within one partition and exchange places of all the guys in the other partition. That will not change the partitioning. And so that's why there is n1 factorial and 2 factorial down there. That's a large number, right? So even bipartitioning, if n is large, you just cannot do it straightforwardly. In fact, there is a formula if you want to divide your graph, your n nodes or n objects into k non-empty group, and that this formula will have a name. It's called Stirling numbers of the second kind, and I just put it here so you would realize that, well, yeah, this is factorial, right? So this is k factorial divided by j factorial, k minus j factorial, and this is the power of n, right? And if I want to calculate the total number of possible clusters or non-empty groups, I'll actually need to try all kind of partitions, partitioning the graph into 2 groups, 3 groups, 4 groups, 5 groups, up to n. And that means, adding this together. And this will give us total number of possible partitions. It's called Bell number. Now, this is huge. And if you try to just calculate it, say with 20 nodes, the total number of all possible combination of those nodes in different groups, it's actually here. So this is like thousands, millions, billion, well, trillion, right? And it's only for 20 nodes. So yeah, we can just forget going through all the possible combinations and trying to figure out how to split this into communities. Pretty much all algorithms that exist out there for graph partitioning, they're either pure heuristics, which means there is something we know in practice work, or they're greedy algorithms, which means we're not trying to go through all the possible combinations. We just have some objective. We're trying to optimize, and we're doing it in a greedy fashion. In a greedy fashion means on every step, we're not looking ahead. We're just optimizing what we can on that step. So quite often it's local optimization. Those greedy algorithms, like in every other situation, they usually they will not lead you to an optimal solution, but quite often they're pretty good. And that's sort of the approach we're going to be taking. Today we're going to talk about the heuristic algorithm, and this is kind of cool algorithm that actually physicists came up with. The early 2000s, and it caused a lot of stir in the community because it was sort of obvious, but nobody had done it before. So the idea is the following. what we're doing is we're actually trying to find the sort of the weak edges between communities. So we're trying to find those sort of places, in the graph that are weakly connected. And the way to think about it is the following. If we look at this picture, you realize that those edges that connect communities, they actually act as bridges, right? And as bridges, they'll have to carry lots of traffic. Pretty much every time you want to get from every node to from the node in one community, right, to the node, to any node into another community, you'll have to cross this bridge. Now, sort of the traffic analogy in terms of graph would be, well, shortest paths. So those bridges that connect different communities, they will have lots of shortest paths going through them. Now, if you remember a little bit, a few lectures back, we talked about the centrality metrics. And there was one centrality metric for the node that is very similar. So we talked about betweenness centrality, right? And betweenness centrality was defined as, for the node, we calculated it by the total number of the shortest path that goes through this node. Well, you can actually, nothing prevents you from extending this definition to actually edges. And Mark Newman and Newman-Girvin, they actually did this. They extended this traditional definition from sociology, the definition of node betweenness, so the betweenness centrality, onto edges. And the extension is obvious. What you need to do is you just need to calculate the total number of shortest path that goes through every edge, right? Now, it is also it is computationally intensive, and because of that, again, this method, though very pretty, is very easy to to code, but it works well only for the smaller graphs, again, because of computational complexity. But it's very, very nice and very clean idea. So the idea is the following. We define an edge betweenness as a number of shortest path that goes through a particular edge. And for every edge, we calculate that value. We then realize that those edges that connect communities, those edges that are between communities, will have the largest value of this edge betweenness. And then we can just remove them. And by removing them, by removing those bridges, we'll split the graph into communities. So here is the algorithm. For every edge, compute edge betweenness. Oh, and by the way, I formulate this now as algorithm for several reasons. One is, well, we're actually getting into sort of algorithmic part of the class, where we'll talk more about algorithms. And the other reason is, by whatever sort of surprising reason, network X has very, very few graph partitioning algorithm implemented. It's probably coming in the next release, but it's not there. And so that means, for the homework and for you, there will be homework on actually implementing those algorithms. So there you go. Okay, so the idea is very simple. For every edge, we compute edge betweenness. And then we remove edge with the largest betweenness. And we do it until any edge is left, right? that will create a dendrogram or a tree very, very similar to hierarchical clustering, sort of in a nature. Now, there are a couple subtle points here. One point is the following. Let's say we have this graph. I'll draw it. So, and let's say we calculate edge betweenness. And on the very first step, we found that, say, there is this, the edge betweenness, the largest for this edge, and so we cut it out. So what's left is sort of this piece. What we need to do then is to actually recompute edge betweenness, because after we remove this edge, the routes could have changed, and there might be other edges that are not as obvious as these two guys that are up for removal. So that's one point. Another point is we could actually build this into bipartitioning algorithms if we want, nice tree, nice dendrogram tree. So the way to do that is the following. Say we do. Let's say we calculate the betweenness, right? And we sort edges, and we start removing. And then we remove this edge, and then we calculate components, calculate connected components. If we remove this edge, actually I can probably erase it, yeah. If I remove this edge, there is still a connected, the graph is still connected. Let's say the next edge for removal is this one. I remove it, and now graph is split into pieces. And the connected component algorithm will, of course, detect this change, and now we'll have two components. And then you can work in a sort of typical classical hierarchical manner, which is, okay, well, now you have two components, and you just take this algorithm and apply it to each of the components separately. Okay? So that will build, that will help you to build a dendrogram, a tree, because you'll start with one big component, then it splits in two, and etc., etc. Now, there is, one question remains here, is the following. Well, the same as with hierarchical clustering, when you get this sort of dendrogram tree, you'll need to somehow decide where were components, because you eat edges on every step. Well, by the end, the graph is gone. Sort of you got the tree, but where were those sort of communities? The other thing is opposite to hierarchical clustering. We're actually doing what's called opposite to agglomerative clustering, because in the case of Similarity, we did agglomeration. We looked at the pairs of nodes and combined them together to build the whole graph. Here, we're actually doing divisive clustering. So we're starting with the whole group, the entire graph, and then start splitting it into pieces. And so, in fact, to get communities, in this case, we don't need to go all the way down, right? So we can stop after a few sort of iterations. But the question is, when to stop? In some sense, this question is very analogous to the question, okay, how many clusters? Just sort of different look at the same problem. Well, to do that, and by the way, this is sort of dendrogram we're going to get when we do this hierarchical clustering. Well, to measure the clusters, the quality of the clusters, we can use some metrics, and one of them we're already familiar with. It's modularity. Now, remember, modularity calculated assortative mixing for the nodes. But here, we're literally facing the same problem, because creating communities is about assigning a label to a node. And what we would like to have is the nodes, sort of the nodes in the same community should have the same labels, right? And they should be connected. Now, if all of them totally interconnected, that's a clique. If there are fewer connections, it's not a clique, but still there should be more connections, more edges inside, in between the nodes of the same color or of the same sort of label, than within the group than between the group. And that's really what modularity will give us. Look, delta CICJ is a Kronecker delta, and it means if the classes of the node I and node J coincide, it's 1. And if they're 0, if they're not coincide, if they're different, it is 0. So what this sum does, this piece of the sum, is really just adding up all their edges that exist in the graph, and Aij means the edges exist in the graph. But the Kronecker delta makes sure that we're adding up only those that belong to the same cluster. Right? So if an edge connects two different clusters, this is, say, node I, and this is node J, well, Kronecker delta will be 0, and so this edge will not be taken into account. So this part of the sum is just adding up number of edges within clusters. And here, as we discussed last time, what we do is we subtract. This is expected number of edges if the graph was random. Now, this is so-called null model. If you think about statistics, we would like to compare some values to the null model. And if everything was random, we would have on average that many edges within the cluster. And this is how many edges we do have. And so the idea is that the score, the modularity score, will tell us how much more edges we have within the cluster compared to if there were no cluster there, if we just had random connectivity. And in this sense, the higher the modularity score, the better are the communities, or the more modular things are. Now, because it is normalized, it's within the range from -1/2 to 1. It's just a little bit weird range, but that's the way it's defined. If we have a single class, it's actually going to be 0. And so we can actually think of this modularity as starting from 0 and then growing, and then when we have sort of that, when we're overcutting into pieces, it will decrease. And so we can actually try to detect this point when the modularity, this is modularity, when the modularity is the largest, right? And this is number of clusters we do. So what we can do is, while we're removing those edges, we can monitor the values of modularity. And when we sort of detect that we pass the peak, we can stop. And that will be sort of the most, the most quality, well, the best quality clusters. Now, this is just one of the possible metrics, and again, we'll discuss more metrics to deal with clusters next time. But this one is quite popular. So this is the same quadratic graph as I shown before, and here it's modularity. Well, it's just sort of on the side, And you can see here the authors used the Betweenness to build the entire graph and measure modularity on the different levels. And what's shown here is the modularity for this particular graph has this kind of funny shape. All right, it goes up, then there's this thing, and then it decreases. And so in some sense, based on the modularity, there are probably, there are two different sort of cutting levels that make sense. So one is right there on the very top, which really, if we follow sort of this cut line, that will literally just split graph into two pieces, and that corresponds to this cut. Or there is another one a little bit below that will actually separate graph into 1, 2, 3, 4, 5 communities. Okay, and so based on the modularity metric, this is the best split for this particular graph. Now, I actually did this sort of clustering on a smaller graph. Well, in my case, the maximum modularity happened not with 5, but with 6 nodes. Now, this is just a visualization, though there is an overlap in colors here. Every node still belongs only to one cluster. I'll go back for a sec to okay, to this picture. So what happened is the optimal modularity would actually correspond to almost this partition, right? There is this node 33, 34, and there was this 26, 25. So there's these guys, there's a big blob here, blob here, and let's cut it out this piece, right? So going to this picture, yeah, that's what we pretty much have, right? Though, again, historically, a karate club did split somehow this way. There are more structure in the data than just split, because it's clear that within the karate club there are sort of subgroups. And modularity metric gives us this as the best partition. Okay, so to sum up, we talked about, first of all, we talked about the ways to do sort of, we talked about what clustering, what communities are, and we looked at two different ways. One is to actually do similarity-based clustering, and the second is we started looking at the graph partitioning, and we did today a very simple heuristic method, and it's heuristic because, well, we just decided that it would be a good idea to remove sort of bridges between groups, but there is no good optimization function that we are optimizing. There is no sort of consistent optimization. There is no guarantees in here. It just seems to work. Both of those methods are very clean in terms of the ideas used. Unfortunately, both of the methods are quite computationally intensive. In order to build a similarity matrix, you need to calculate pairwise similarity between every pairs of nodes, and then a hierarchical clustering is n cubed. In the simplest implementation, it can be done n squared log n, but it's still there is n squared in there, and you can trick these things. You can use a lot of techniques to make it better, but it is computationally intensive. This method also requires betweenness calculation between all pairs of nodes. I'm sorry, betweenness calculations for every edge, but the betweenness calculation for every edge, you have to go through all the pairs of nodes in that calculations, and it's again quadratic in this number. Again, you can sort of make things better. There are algorithms that allows you to calculate betweenness much faster, but it's still not the method of choice, because and honestly, at this moment, very few people are interested in clustering on networks, on network communities in the network of 30 people. It's interesting to partition, Facebook graph. It's interesting to partition, graph with millions of nodes. It's interesting to partition call graph. Think about how many people using, say, MTS or Megaphone or etc. So the scale is much, 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 much larger, and so somewhat different approaches needed. Needed approaches that has some sort of theory behind it, and something that is actually scalable in a sense that the performance is not worth that O of n, or better if it is even less than that. And these are the type of algorithm we're going to talk about next time, things that are sort of very, very practical. So a few references. If you're interested in this topic, I strongly recommend you to look at this review, Community Detection and Graphs, and there is another review, Graph Clustering. In fact, these are also sort of, as we've seen many, many times in this course, because people come from different background, the terminology, quite often they use sort of different terminology to define the same thing. So those papers is about community detection. At this moment, probably community detection is, or communities in networks is sort of the most stable terminology and widely used. And people quite often refer to graph clustering in terms of the sort of the way to find communities through graph similarities. And here are the two papers by Mark Newman, one about betweenness centrality and the other one about modularity and evaluating community structure. So again, these are pretty big reviews. They're I think 70 pages each, but they have tons of information and references. So strongly recommend it. That's pretty much it for today. Questions? Okay. Well,